Welcome. Today we are looking at how three major technologies work together: OpenFlow, OpenStack, and OpenDaylight. The title of this section is Combining OpenFlow and OpenStack with OpenDaylight. What we will explore is a management plane framework for software-defined networks. More importantly, we will follow the complete journey of a tenant's request, from the moment they ask for virtual machines all the way until those requests become concrete flow rules installed in physical switches. Let's begin with the fundamental problem. Network virtualization can be implemented at many different levels and by many different technologies. You can virtualize at layer 2, layer 3, or even higher. You can use overlays, underlays, tunnels, or pure OpenFlow. The challenge is making all of these technologies work together seamlessly. That is exactly the job of the management plane. Frameworks sitting in the management plane provide the coordination layer that ties everything together. The goals of any good management framework are consistency, efficiency, performance, reliability, and security. OpenDaylight is one such framework. It was designed specifically to manage virtual networks in an SDN environment. To do its job properly, it must support 5 core functionalities. First, continuous monitoring of the network. Second, intelligent scheduling of resources. Third, efficient resource allocation. Fourth, the ability to adapt dynamically when conditions change. And fifth, strong policy enforcement so that the network always behaves according to the rules defined by the operator or the tenant. So what exactly is OpenDaylight? It is an open source project that develops a modular, pluggable, and flexible SDN controller platform. The controller exposes open northbound APIs so that applications sitting above it can talk to the network in a clean, standardized way. Applications use the controller for 3 main purposes. They gather network intelligence, understanding the current state of the topology and devices. They perform analytics on that data. And they orchestrate new rules that change how packets are forwarded. The key design idea is dynamic modularity. Modules that perform specific network tasks can be plugged in or removed at runtime as needed. A quick historical note. The architecture we are studying is the Hydrogen release, OpenDaylight's very first official release in February 2014. It was built by roughly 50 organizations and contained over 1 million lines of code. The project itself had been founded under the Linux Foundation just under a year earlier, on the 8th of April 2013. Now let's look at the architecture itself. OpenDaylight is organized into 5 clear layers. Always read the stack from top to bottom. High-level intent enters at the top, and concrete flow rules leave at the bottom. At layer 5 we have the network applications, orchestration systems, and services. These include the management GUI and CLI, the VTN coordinator, defense for all for DDoS protection, the OpenStack neutron service, the affinity service, and ODMC. These applications talk to the controller through OpenDaylight's northbound APIs, primarily REST. Layer 4 contains the base network service functions. Here you find the Topology Manager, Stats Manager, Switch Manager, Forwarding Rules Manager, Host Tracker, ARP Handler, VTN Manager, and the Neutron OVSDB plugin. Layer 3 is the Service Abstraction Layer, or SAL. This is the critical hinge of the entire architecture. It contains the Plugin Manager, Capability Abstractions, Flow Programming Services, and Inventory Services. Layer 2 holds the southbound interfaces and protocol plugins, OpenFlow versions 1.0 and 1.3, NETCONF, and OVSDB. Finally, at layer 1 we have the actual data plane elements, OpenFlow-enabled hardware switches, OpenV switches, and any other devices the controller can manage. Let's look more closely at the 6 base services that sit in layer 4. These services handle the fundamental management tasks for network devices. Additional services can of course be added later. The Topology Manager builds and maintains the network topology, essentially the controller's live map of what is connected to what. The Stats Manager collects statistics from the devices. These statistics form the feedback signal that enables monitoring and dynamic adaptation. The Switch Manager handles all southbound device information. It maintains the inventory of switches and their capabilities. The Forwarding Rules Manager is responsible for installing flows on the southbound devices. This is the point where high-level policy is finally translated into actual packet forwarding behavior. The host tracker keeps track of all connected hosts, knowing exactly where each endpoint is currently attached. Finally, the ARP handler processes ARP messages on behalf of the controlled network, preventing unnecessary flooding. Notice the clean division of labor. Topology Manager, Stats Manager, Switch Manager and Host Tracker primarily observe the network. The Forwarding Rules Manager and ARP Handler act on the network. Every higher-level application built on top of the REST API ultimately relies on this combination of observation and action. The Service Abstraction Layer is the true hinge of the OpenDaylight architecture. SAL is what allows a single, stable northbound API to drive many different kinds of hardware underneath. Applications simply request a desired outcome. SAL then decides which southbound plugin is capable of delivering that outcome and routes the request accordingly. Its main responsibilities are managing the plugins, providing capability abstractions, handling flow programming, and maintaining inventory. Below SAL sit the concrete southbound plugins. OpenFlow 1.0 and 1.3 are used to program flow tables inside switches. Version 1.3 is significantly more powerful. It supports multiple flow tables with pipeline processing, group tables, meters, and native IPv4. OVSDB, the Open vSwitch database protocol, is used to configure virtual switches themselves rather than just programming their flow tables. NETCONF provides a standards-based way to configure additional virtual and physical devices that sit in the data plane. One important lecture caveat: the figure we are studying shows the original API-driven SAL. In later releases, OpenDaylight replaced it with the model-driven MD SAL, which binds Yang models to Java objects. The older ADSAL was eventually deprecated. OpenDaylight was originally released in different editions targeted at different use cases. The architecture shown in Figure 6.12 is the Virtualization Edition, designed specifically for data center environments. This edition bundles the OVSDB southbound plugin so that the controller can properly configure Open vSwitches that form virtual networks. It also includes a Neutron bundle that supports both VXLAN and Gray tunnels, making it suitable for OpenStack and Cloud Stack deployments. On top of the base platform, the Virtualization Edition adds 4 important components. VTN, Virtual Tenant Network, which provides multi-tenant virtual networking directly on the controller. Neutron support, including the Neutron OVSDB bundle for OpenStack integration. Defense for All, sometimes labeled D4A, which is an SDN application for detecting and mitigating DDoS attacks. And finally ODMC together with the Affinity Service, the OpenDove Management Console, in a service that allows operators to express relationships between workloads. A quick note on 2 OCR errors that sometimes appear in the original figure caption. Defense for A sharp production should simply read Defense for All, and OCSDB should read OVSDB. Also, protocols such as Lisp, BGP, PCEP and SNMP belong to the Service Provider Edition, not the Virtualization Edition shown here. Virtual Tenant Network, or VTN, is one of the most powerful features in the Virtualization Edition. VTN allows users to design and deploy an entire network without any knowledge of the underlying physical topology. The user simply describes the logical network they want. VTN then automatically maps that logical network onto the real physical switches. Looking at the architecture, at the top sits the VTN application. It communicates via a REST API with the VTN coordinator. The coordinator contains an ODC driver and, through further REST calls, one per controller, talks to the VTN managers that run inside each OpenDaylight controller instance. Those managers finally program the physical switches. The VTN coordinator is an external application. It presents a clean REST interface to the user and is capable of orchestrating multiple controllers. This means a single virtual network can span several OpenDaylight controller domains. The VTN Manager is a plugin that lives inside each controller. It handles PACKETIN messages, maintains host information, and installs the necessary flow entries into the OpenFlow switches. The ODC driver is responsible for translating the high-level commands coming from the coordinator into instructions the manager can understand. The key scalability idea is simple: one coordinator can manage many managers. That is how VTN scales beyond a single controller. Before a virtual network can be realized, the system must solve the virtual network embedding problem. A tenant submits a virtual infrastructure request. This request contains three things: the desired topology, the resource requirements of every virtual node, and the bandwidth requirements of every virtual link. The nodes may be virtual machines, virtual switches, routers, or firewalls. The links carry bandwidth demands. A scheduler must decide exactly how each virtual node and each virtual link will be mapped onto the available physical resources. Once the mapping decision is made, the system allocates the resources. It schedules the virtual machines, creates the virtual switches and routers, and installs the corresponding forwarding policies in the OpenFlow switches. The primary objective is to maximize the acceptance rate of incoming requests while simultaneously minimizing operational costs such as energy consumption. Unfortunately, the virtual network embedding problem is well known to be NP-hard. In fact, it is strongly NP-hard even when all demands are uniform. Because of this complexity, practical systems rely on heuristic algorithms rather than exact solutions. The canonical survey paper on this topic is the 2013 IEEE Communication Surveys or Tutorials article by Fisher, Botero, Beck, Demir and Hesselbach. Now we put the entire picture together and follow a tenant request all the way from submission to installed flow rules. Remember the division of responsibility. OpenStack schedules the compute resources, while OpenDaylight schedules the network resources. Neither system alone can deliver a complete virtual infrastructure. The process unfolds in 5 steps. Step 1. The tenant submits the request to OpenStack. The virtual infrastructure request arrives and Nova, OpenStack's compute service, schedules the corresponding virtual machines in the data center. Step 2. The network portion of the work is delegated. The scheduling request is sent to OpenDaylight through its REST API. Step 3. OpenDaylight solves the embedding problem. It then uses OpenFlow controllers and the OVSDB protocol to create the virtual network components and install the necessary forwarding rules in the switches. Step 4. The resulting state is recorded. The virtual network topology is written into the Topology Manager, and information about the virtual network components is stored in the Switch Manager. Step 5. Continuous monitoring begins. The Stats Manager watches the status of the new virtual network through the Service Abstraction Layer. Importantly, this is not a one-time process. There is a continuous feedback loop. As operating conditions change, the allocation can be re-evaluated and adjusted. Why does this loop matter? Because a tenant may need to scale their infrastructure up or down at runtime to respond to fluctuating demand. Embedding is therefore never a purely static, one-shot decision. Let us close with 4 essential points to remember from this section. First, the service abstraction layer is the whole idea of OpenDaylight. Northbound REST APIs remain stable and consistent, while southbound plugins, OpenFlow, OVSDB, NETCONF and others, can come and go. This indirection is what makes the controller truly modular and future-proof. Second, VTN cleanly separates the logical network from the physical network. A tenant can design a complete Layer 2 or Layer 3 network without any knowledge of the underlying substrate. The coordinator and its managers then map that design onto real switches, even across multiple controllers if necessary. Third, cloud and SDN systems deliberately split the job. Nova is responsible for scheduling compute, OpenDaylight is responsible for scheduling the network, and Neutron acts as the seam that joins the two worlds. Delivering a complete virtual infrastructure always requires both halves working together. Fourth, virtual network embedding is NP-hard and is never truly final. Heuristics are used to decide the initial mapping. After that, the continuous monitoring provided by the Stats Manager feeds the runtime decisions that allow the network to scale up or scale down as conditions change. A final historical note: the figures we have studied, 6.12 through 6.14, depict the OpenDaylight Hydrogen release from 2014. The concept of separate additions was later dropped, and the original ADSAL was replaced by the model-driven MDSAL.